Small satellites, like this standard CubeSat, have made access to space relatively cheap. But that compact, briefcase-sized frame inherently limits what the spacecraft can actually do once it reaches orbit. To perform complex missions, spacecraft require two distinct types of movement. They need powerful, high-energy bursts to quickly change position or climb in altitude, and they need ultra-efficient, slow propulsion to cross massive distances over time. The problem is that these two flight profiles rely on contradictory physics. Rapid acceleration requires combusting a chemical fuel, while highly efficient cruising relies on electrical acceleration. Each method requires entirely separate hardware. Because engineers cannot fit both systems into a tiny chassis, small satellites are locked into a single mission profile. They have to choose between traveling far or moving fast. If you try to force both capabilities into a microsatellite, the internal geometry fails. Housing separate tanks, redundant valves, and two sets of plumbing consumes almost the entire internal volume, leaving almost no room for the cameras or sensors the satellite was built to carry. On top of the lost space, carrying two disparate types of fuel, a chemical propellant and an electrical one, incurs a heavy weight penalty. Every gram matters in a rocket launch. The combined mass of redundant propulsion systems quickly pushes these tiny spacecraft past the strict weight limits required to keep their launch costs viable. To build a multi-role small satellite, engineers needed to solve this physical real estate problem. They needed to eliminate the redundant plumbing entirely by finding a single liquid that could burn like a chemical rocket and accelerate through an electric field. Inside the MIT Space Propulsion Laboratory, researchers have been working for years to scale down electric propulsion systems so they can fit on smaller satellites. Their designs rely on miniature electrospray thrusters, which are powered exclusively by a specific class of chemicals known as ionic liquids. In the vacuum of space, this stable fluid acts as a pure sea of ions ready for manipulation. Separately, the U.S. Air Force developed a fuel known as ASCENT. It was engineered purely as a safer, less toxic combustible alternative to traditional chemical rocket propellants. While reviewing the properties of ASCENT, a team led by MIT's Amelia Bruno noticed a critical chemical overlap. At its atomic level, the ASCENT propellant is an ionic liquid mixture. This structural similarity led to a straightforward hypothesis. If ASCENT shares this exact chemical structure, it should be possible to take a highly volatile chemical rocket fuel and manipulate it using electric fields. To test this, the team placed a magnetic levitation platform inside a large vacuum chamber. This setup simulates the frictionless environment of open space. They mounted thumbnail-sized electrospray thrusters onto a test CubeSat. Each thruster drew from a reservoir the size of a Lego brick, containing just 1 gram of the ASCENT chemical fuel. Looking at this cross-section of the microthruster, you can see what happens when voltage is applied to the liquid ASCENT reservoir. The electrical charge physically strips individual ions from the liquid. Those charged particles are accelerated and ejected through microscopic openings to generate thrust. The researchers ran the thrusters continuously for up to 100 hours. The expelled particles generated enough force to physically spin the levitating CubeSat, matching the efficiency and performance of conventional electric fuels. This single test solves the physical volume problem. The data proves that high-thrust combustion and high-efficiency electric acceleration can operate effectively from the exact same drop of fuel. NASA is now taking this laboratory breakthrough and applying it directly to flight hardware for the upcoming Green Propulsion Dual-Mode mission. This mission uses a unified plumbing architecture. One central tank of ASCENT seamlessly feeds both a primary chemical thruster in the center and 4 tiny electrospray thrusters on the periphery. Combining these systems opens up deep space destinations. A tiny spacecraft can now use its electrospray thrusters to slowly and efficiently push itself across interplanetary distances while barely consuming its reserves. Then, once it arrives at its target, it can ignite the main chemical thruster using that same shared tank. This provides the sudden braking power needed to enter orbit and maneuver for scientific observations. With a dual-mode system, a relatively cheap, briefcase-sized satellite can finally mimic the complex, multi-stage flight profiles normally reserved for massive multi-billion-dollar interplanetary probes. This architecture also applies to missions closer to home. Constellations of small satellites tracking severe weather could use chemical thrust to rapidly reposition over a storm, then use electric thrust to efficiently loiter in place. The final engineering hurdle is moving from the controlled conditions of an MIT laboratory into the harsh, unpredictable radiation and extreme temperatures of actual orbit. Its upcoming launch to space will serve as the ultimate crucible for the shared plumbing, valves, and ASCENT fuel. By stripping away redundant hardware and proving one propellant can serve two masters, engineers have upgraded the CubeSat from a simple low-orbit tool to a highly capable explorer.